All right, so in this video, we're going to talk about using some antiderivative formulas. Remember, there's only a certain amount we know at this point, and these formulas, or these tables sometimes are referred to, can be helpful in taking advantage of some shortcuts along the way. Now, I'm not normally a big advocate for memorizing formulas or looking at tables to do a lot of these things. But to get started, I think this is a good opportunity to really see where things are going to take us in the future. So I'm gonna be a little bit lax on allowing the use of these formulas at this stage of the course, at least. So the formulas are on page 233. It's table 4.2. You can take a look at it. I'm going to work an example now with it, and you'll be able to pick up pretty quickly on what I'm talking about. So the example we're going to look at is 2 cosine pi x dx. Now, the big difference and the main reason why we need these alternative general derivatives is because we've got a pi x sitting in here. We've got a composition essentially, and we can't decompose it our normal way of just adding one and dividing or using our trig derivative chart. So the formula that comes along with this one, and it's, if you're keeping track in the book, it's equation 3, or it's number 3 in the table. We know that the integral of cosine kx dx is going to be 1 over k sine of kx plus c. So our k value in this particular problem is pi. So when I integrate this, my 2 is still going to be there because essentially I can pull that outside. But when I integrate this, I'm going to get a 1 over pi sine pi x. So we've got our 2, we've got our 1 over pi sine pi x, and then followed by a plus c. So again, our k value here is going to be pi from that problem up there. Okay? So using the table, it's just more or less extracting the information that you need. You would, of course, simplify. And there you go. There's your final answer. Before we move on, though, I would like to work this one with you guys and check and kind of move backwards and show you that it is, in fact, accurate. So if I take the derivative of this, I'm going to have my 2 over pi cosine pi x back times the derivative of the inside, which is pi, and then the derivative of a constant is 0, and now the pi's divide off, leaving us with just the 2 cosine pi x, as we should have expected. So again, just taking a look at these formulas in the book especially, they're really not any different for any of the other trig functions. If you've got that kx on the inside, you're going to end up dividing it out here to start once you come up with the antiderivative. Okay, so we'll take a look at another example. Another one where it's very similar. We'll use that table. If you look at the table, equation 2 talks about how the integral of sine kx dx is going to be the negative 1 over k cosine of kx plus c. The negative comes from the fact the integral of sine is negative cosine, and that 1 over k, like I pointed out in the last example, comes from this guy here. So for us, our k value is going to be pi over 2. So therefore, when I divide by a pi over 2, that's going to be multiplying by a 2 over pi. Okay, so this k value here, I might as well write it out. The k value is pi over 2. So when I divide it by that, that's the same thing as multiplying by 2 over pi. And then we'll have our cosine. We'll have our cosine of pi over 2x plus c. Cleaning it up a bit, we get negative 2 over 3 pi cosine pi over 2x plus c. So again, let's just take a moment and confirm that this isn't truly the antiderivative by taking the derivative of it and hoping it takes us back to where we started. So if I take the derivative of this thing, I have my negative 2 over 3 pi. Going to have a negative sine of pi over 2x back times the derivative of the inside, which would be pi over 2, and then the plus c goes off to 0. So when this thing is simplified, the pi's go away, the 2's go away, the negatives do away with each other, and all that we have left is the 1 over 3 sine pi over 2x, as we hoped.